Bueno, ahora sí entonces le damos la palabra a Eivind Grov. Él es jefe científico, Chief Scientist de SINTEF, una de los centros de investigación más grandes de Europa.
Yeah, not bad. Anyway, good morning, everybody. Thanks a lot, Matthias. SINTEF is actually a research company. It's actually a foundation. It was established 75 years ago, and we are actually celebrating this event these days. It was established because some professors at the university in Trondheim thought it would be favorable to have a unit which is only related to applied and industrial research, whilst the university should be or shall maintain the responsibility for basic research and education. So these two entities have been going in parallel for 75 years. And a lot of people, like myself, I have my main position at the university, at the SINTEF, and I've had an adjunct professorship at the university. And that goes for a lot of people. We are about 2,200 people working in SINTEF today, covering basically every topic that you can imagine, which is related to natural sciences. But we are not a design company, so our contribution to such as subsea tunnel projects are through positions as technical advisors to the owners, basically. And that is how we have been involved in a number of different subsea road tunnels in Norway as well as globally around the world. So I will come back to that during my presentation. Wrong way. Yeah, I graduated back in 1983, so I have been more than 40 years in this tunneling business. I'm officially retired, but I do these kind of things that we are doing now because I think this is really, really fun. I have had a lot of positions within societies like yourself, the Norwegian Tunneling Society. I've been president in that organization. I've also been a vice president of the International Tunneling Association, even running for president some time back, but didn't win, unfortunately. And I've been working with subsea tunnels in a number of different countries. Some have been executed or constructed, and some have been only nice plans for the shelves. So I will talk about subsea tunneling. I will try to focus on what makes this different to an ordinary land tunnel. That is kind of the approach that I'm taking. But I would like to bust a myth. Well, actually, I could bust two myths. One is that a lot of people tend to believe that Norway is full of money, like Onkel Skrue in Donald. I don't know what you call him in English. But we are not. The second myth is that some people tend to believe that in Norway it's just good rock, excellent rock. You can build whatever you like in caverns and tunnels. That is also a wrong impression. We do have good rock, yes we do. We do have hard rock, yes, but we have a lot of mixed rock conditions, which is due to the fact that folding and faulting and high tectonic stresses are influencing what we have as a construction material today. But we have learned that when we consider the rock mass as a construction material, and we do take the benefit out of the excellent properties this material can have, still being aware of that there could be a lot of fault zone, there could be a lot of poor quality rock, and so on. We have something that we can utilize for a number of different applications. Building large caverns like you saw, the Stadship Tunnel, or large caverns like Gjøvikål, long tunnels, and so on and so forth. Did I bust that myth? Is that okay with you now? It's not only excellent, fantastic, good rock. It's a lot of different rock mass qualities that we have to face. And we have to face it also when we are going forward with subsea tunnels. And I'll tell you why. This is looking from one side of the fjord and over the sea and to the other side. We basically do not know exactly what is in between the two portals that we are going to make the tunnel. We know that we have to go down, go under the sea, and up again on the other side. This we see, this we see, this we don't see. But we do have certain investigation methods that allow us to see in brackets using different types of technologies. Also, there is a situation which is illustrated that we have large amount of sediments which are actually covering the top of the bedrock. And to some extent, that level or that package of loose material is something that we could see through. Sometimes it's difficult to see through it. So we have to have different types of investigation methods. Often in Norwegian fjords, and I would guess that is also the situation here in Chile, there is a fault zone or two or three somewhere under that sea that we have to face. So we need to have investigations or investigation methods that allow us to see this. We have inclined tunnel from both sides. This is a kind of an old figure because it says 8%. That would not be allowed today. It would be not more than 6, I would think. But that is not something which is absolutely carved in stone either. Isn't it so, Arild Petter? But larger than 8 would be difficult. And the leakage potential is infinite. If we have a puncture through, the theoretical amount of water that could flush into the tunnel is infinite. And the water which leaks in is very often saline. It's saline water, which means that we have to take some precautions to avoid corrosion, for example, on these different measures and things that we installed in the tunnel. The rock cover is a critical parameter. What is the minimum rock cover? Today, the Public Roads Administration has a minimum requirement of 50 meters, which means that this thickness here should be no less than 50 meters. That's a recent requirement that has been installed. But we do have a lot of tunnels, as you can see, with less than 50 meter rock cover. But the 50 meter rock cover is a kind of safety requirement. But as I said, there are a lot of tunnels with less than 50 meters. Still working very well. And to give some explanation to these dots here, they are representing the seismic velocity, which have been found from seismic refraction survey or seismic reflection surveys. And you can see the R means that instabilities of there are certain points here which have had a kind of instability when doing the construction phase. Minimum rock cover is a critical factor. We do have to do certain investigations, and many of these are things that you know from before, from doing tunnels on land. The main thing here is that we have to assess the geological risk, and we will come back to that later on. But we also know from tunneling in general that it is not viable at all to try to minimize or to reduce the risk to zero. No matter what kind of tunnel you are building, that is not possible. That's not viable at all. Then you have to build one tunnel to investigate for the tunnel you are going to build, where you built the tunnel. And that doesn't really work. And this goes, of course, for subsea tunnels also. But what we have to do, we have to be able to identify and manage these risks properly. And that goes even far further for subsea tunnels than compared to a land tunnel. This picture shows how we do, in principle, refraction seismics in the sea. Many of you are familiar with what they call hammer seismics, or which we call refraction seismics. You lower a cable with hydrophones to the sea floor, and you do initiate the sources using small portions of explosives. And this will give us an indication, do we have weakness zones, fault zones? What kind of velocity could we expect these fault zones to have? It gives us the depth of the different sediment layers. Refraction seismic investigations, and particularly in locations where we do believe or where we do expect that there could be some faults or some adverse ground conditions. Arild Petter was touching base on the different stages, and typically also for an ordinary tunnel as well as a subsea tunnel, there are different stages with which we are doing different types of investigations and with different levels of investigating. Some of these may not necessarily be necessary for a land tunnel, but the fact that such as reflection seismic investigations and refraction seismic investigations are those that we mainly use for subsea tunnels, plus directional core drilling. Directional core drilling has turned out to be a very useful tool for us, and I will show you later on in the presentation why is that. These are just giving some numbers, how much of the different projects have or are covered with refraction seismic and reflection seismic. We don't need to spend too much time on the details here. We just have to state that these are investigation methods that we rely very heavily on, and which are something that may not necessarily be done for an ordinary land tunnel. This is directional core drilling. Some of you may know the company Devico, which I believe has had its presence here in Chile and still has. They are doing, or they are manufacturing equipment for directional core drilling. It basically means that you can bend your core hole like a banana if you like. This picture is from a project called Bømlafjord project, which is south of Bergen. I can use this one probably. This is the expected or planned tunnel alignment. There was an expectation that something could be hiding here in this area. So they did a core hole, and what they actually met was some moraine in the core hole over here. They pulled back the core bit, and they restarted the core drilling to a lower level in this area, and then they saw that, okay, we are lowering the core hole, and we avoid this unfortunate situation there. And the consequence was that also the tunnel alignment was lowered slightly also. So that is a way that we are doing directional core drilling, to be sure that we are placing the tunnel at the given level where we are not interfering with weak zones, which could go deep. There is one picture here. This is from the Oslofjord tunnel. And this is actually the reason why we are doing this procedure today. Because when we were planning the Oslofjord tunnel, we had the tunnel level here, and we had two core drillings. One was directional drill and one was straight. And they were located basically in the level of the planned tunnel. Unfortunately, in this area, the soil was actually going deeper than what we expected from before. So when they came to this location with the tunnel itself, they discovered that based on drilling probe holes ahead of the tunnel phase, they discovered that, wow, it's not rock ahead of us. It's basically soil material. So they stopped the tunnel excavation. They made a bypass on a deeper level, and then they had to freeze this zone to be able to go through it later on. From that time on, we have always put the directional drill hole above the tunnel level to secure that, or to ensure that we are not repeating that mistake, because that was a costly mistake. But thanks to the people who are actually doing the probing ahead of the tunnel phase, and those who recognize the fact that this is going to be a zone that we are not able to just go through with the ordinary excavation, they stopped the construction and decided to do the bypass. If they had just went into that with the open tunnel phase, that could have been a big disaster. So it means, and this is one thing that we have to keep in mind, when we are doing subsea tunneling, we have to keep the guard quite high. If we lower the guard, we will be knocked out by the ground conditions at the first possible occasion. So keep the guard high, which means do the probing ahead of the tunnel phase and read and understand what the rock mass is actually telling you. Oh, wrong direction, sorry. We have a risk-sharing principle in Norway, and this risk-sharing principle also goes for subsea tunnels. It basically means that there is a lot of risk on the contractor and there is a lot of risk on the owner, but it's fair and square shared. The owner carries the risk for the rock mass conditions, because we used to say that the owner is the owner is also the owner of the rock mass, because the owner has decided where we're going to build the tunnel. They have decided what to do up front in terms of pre-investigation methods. So they have to take this responsibility. And all the information that has been gathered are disclosed to the tendering companies. So when it comes to the contractor has to carry the risk which is related to the fact that he or is able to do the work within the time and the methods and the means that are expected. He has to have equipment, he has to have manning, and he has to gear up his site to be able to carry out the work in accordance with what has been given in the tender documents. We have a beauty in this concept, which is called the equivalent time system, which means that depending on the amount of rock balls, sprayed concrete, and things like that has been done, if it's more than in the contract or the bill of quantities in the contract document, you will have an extension of time calculated using these standard capacity in the equivalent time system. So that's a time regulating method. Which also means that some of the risk with assessing the amount of rock ball, spray concrete, and so on are or is on the owner itself, because he has to estimate these quantities. And the estimation shall be based on the best knowledge at the time that this estimation is actually being done. So there is no tactic in this. There shall not be any tactics in this. And with this system, we claim that the Norwegian practice will give us an optimum price and a minimum price, maybe you can say. If you have a lot of risk on the owner, in a turnkey project, for example, no, I'm sorry, when you have zero risk on the owner, in a turnkey project, the contractor has to take the risk. And you have to pay the contractor for taking this risk. On the opposite, if the owner is taking all the risk and nothing on the contractor, it will also give you a high price. So a balance between the risk taking will give you an optimum price. As I said, it is important that all the expected items are quantified and that it is quantified in a fair way based on the information that the owner has at the time where he is making his calculations. The contractor is reimbursed according to this tendered unit price, and these tendered unit price, they stay valid throughout the contract period, just being adjusted for the inflation. Yeah, I think we have touched base on most of this here. We may say that in a tunneling contract, we have foreseen geological conditions, we have unexpected conditions, and these can be handled by the means and the measures that are in the contract itself. If truly unforeseen conditions occur, then we are in a different spheric, because if they occur, the unit rate contract does not provide a magical solution to it. But a fixed price contract does not either provide a magical solution. In that cases, the success of contract will only be or will depend on how good are the two parties in negotiating a fair and square solution for the problem. And the owner in this kind of situation may take a high risk, because playing the game too hard could lead to the fact that the contractor may ultimately go bankrupt, and then the owner is taking over the whole responsibility and the whole risk of the situation. And that's not a good situation either. So it's important that we are able to share the risk between the parties in a fair and square way. When it comes to risks which are associated with the ground conditions, seismicity and tectonics has been mentioned here already. We have water inflow, weakness zones, rock support, rock mass growing. The most important thing, though, is that whenever we present a tender document in a tendering phase, the contractor must be able to price the risk which is on his hand. We should not put it into a wrapping or disguise the risks, because that will ultimately lead to a situation where the contractor is not able to price the risk. We have had some situations where things didn't go exactly as we wanted. One of them is a tunnel which is called Ellingsøy Tunnel, and this goes back to the late 80s. In this location, we had a rock cover of 45 meters. The water depth was approximately 70 meters, and we encountered a fault zone with clay and lots of seepage. So what happened was that piping actually developed. So this was approximately 7 meter high, cave-in after 6 hours. What had to be done was to try to stabilize. We had to seal off the working face, and we had to place a concrete plug at the face itself to stabilize it. And then when the face was stabilized, we had to do preventive measures to be able to actually go through this with spiling and things like that, to be able to have a This was actually the first fixed price subsea tunnel project ever being built in Norway. Skanska, or Selmer, as was the name at that time, was very eager to do this. It's not a very long tunnel, but what they encountered in this particular project was a fault zone with sandy material. Very high permeability. And what they had to do a lot of comprehensive grouting. They even used tuba machetes to be able to actually grout some of the material in front of the tunnel. Spiling bolts, rock bolts, shotcrete, and going through the secured zone with reduced blast lengths to be able to actually do it. And they had to use shotcrete arches, or what we call today reinforced shotcrete ribs, which you can find in the Q system, for example. Another one was more recent. This is the Atlanterhavs tunnel. They were almost at the deepest point in the tunnel. They were almost reaching down to the bottom. Then they entered into a fault zone. High water inflow, high pressure, you can see. Now, there is no, it's 230 meters below sea level. 230 meters, theoretically, waterhead in that location. So they had a face collapse. They had to cast a concrete plug. You can see the rock bolts here from the instability. So they had to block off that face, cast a concrete plug, and then start again to do short rounds and with extensive rock support when they were moving forward. This took considerably a lot of time, 1 year to actually get through that location totally. But insofar, we have always been able to mitigate the situation and to complete the tunnel construction to a final tunnel. We have never ever abandoned any of these subsea tunnels in Norway. We have basically been using, well, not basically, we have always been using drill and blast. For the Rogfast project, we made a study where we tried to convince the owner that he should look at the possibility of doing the tunnel with a TBM, because we were thinking that a TBM with the EPB facilities or double shield and things like that could be a possible solution, but that was abandoned. And that is the only project where a TBM has been looked at. And the reason why we are sort of hanging on with this drill and blast method is that it provides a great deal of flexibility. We have the possibility to go in with other equipment, other types of equipment, and the fact that at the site we shall always have a mobile formwork to do cast-in-place concrete as a measure if things go wrong. And if you have a TBM, that may be a problem to do so. So that's why we basically have used drill and blast method. Yeah, I'll skip. In principle, this is a little bit old, but we are basically using ordinary rock bolts and sprayed concrete as rock support. Today, there are regulations in the handbook or guidelines from the Public Roads Administration on the minimum thickness and things like that, but this is basically what we are using. Only on rare occasions has there been a need of cast-in-place concrete lining. Oh shit, wrong direction. As I said, water inflow is a risk element in subsea tunnels. There is a maximum requirement on inflow, which is today 30 liters per minute per 100 meter. And that is also the dimensioning criteria for the pump and the pumping system and the drainage system in the tunnel. Because in both land tunnels and subsea tunnels in Norway, we actually allow water to enter the tunnel, but we are taking the water out in a controlled manner. And for a subsea tunnel, which has a low point, it means that all the water which goes in has to end up in the low point, and at the low point, we will have a pumping station and a water magazine. This is kind of a rather large construction element in the tunnel itself. It should be able to store water for either 24 hours or 48 hours of steady inflow of 30 liters per minute over the total length. Not over the total length, how to explain that. 30 liters per minute per 100 meters for all the meters on both sides of the pumping sump. So in case of a electrical failure, so that these pumps which are sitting in here, which they are falling out of operation, the water magazine shall be able to cater for the inflow in 24 hours or 48 hours. And that is sometimes a quite considerable amount of water. Some from this pumping sump, it will be pumped to one of the sides for deployment, but there is a redundancy, which means that the pumping system should also be able to pump to the other side in case there is something. So there is a redundancy in the system when it comes to the pumping, because this is really crucial for the operation of the tunnel itself. We rely heavily on what we call pre-excavation grouting. Pre-grouting. That is something which is mandatory to have established for a subsea tunnel. We do it also for ordinary land tunnels, but for a subsea tunnel it's even more restrictive to have this in place. In many places around the world, people talk about post-grouting. We have abandoned that idea. We say that rock mass grouting shall be done as pre-excavation grouting. And in a subsea tunnel, it's mandatory to have a system for probe drilling ahead of the tunnel phase. Probe drilling ahead of the tunnel phase would delay the excavation process slightly, but that is the first hand of information that we will have when we are doing the excavation work or construction works. Leaving that out is like lowering your guard totally. And the probe drilling is something that we, if we expect good rock mass conditions, we can go down to 2 or 3 or 4 or 5 holes in the probe drilling. If we do expect adverse ground conditions, we will increase the number, and we will probably also increase the we'll decrease the length between each probe drilling round. Annual daily traffic controls the categorization of a tunnel. You will see that in our system, it's average annual daily traffic that decides. In the British system, it's actually the length of the tunnel which decides the tunnel class that we are going to use. So, exporting subsea tunnels is something which is interesting. Some years ago, we were in Qingdao in China, and they had established this. They had established this type of a system: 2 main tunnels and a service tunnel, being excavated using ordinary drill and blast in rock mass ground conditions, which are definitely not far away from what we are used to in Norway. But as you can see, they have a thick cast-in-place concrete lining for all these 3 parallel tunnels. And we tried the best as we could to try to convince them that this is something which is not necessarily for a safe tunnel excavation and operation for this. Because what you actually do is you increase the loading on these structures. So for the tunnel, it has to be designed with full hydrostatic pressure acting on these structures. So we suggested, and we did a lot of numerical models and referring to experience in Norway and so on and so forth. What was the outcome? Was that we were able to take away, they were listening to us, they took away the lining for the central small tunnel, and they kept it for the big tunnels on the side. Yeah, we didn't really win the game, but at least we managed to do something. So I call it a small step for man, a giant leap for mankind. So it's hope to be even stronger in trying to convince people that we have the possibility to do this in a much more, let's say, cost-effective way than many do. So if we go to some locations outside of Norway, since Arild Petter is very focusing on the west coast of Norway, where he is living, I'm focusing very much on Trondheim, where I'm living. In Reykjavik, which is almost at the same latitude as Trondheim, we were involved in a subsea tunnel some years ago, the Kvalfjordur tunnel. And I'll show you some pictures from the Kvalfjordur tunnel. The Kvalfjordur tunnel is located outside Reykjavik. This is Reykjavik, and here is the Kvalfjordur tunnel. This used to be a ferry connection, and you could also go in the fjord here, but this tunnel would cut the distance for all the facilities which are on the western part of Iceland. The tunnel was undertaken by a private company, a private enterprise. It was financed by external funding, no public financing whatsoever, and Spøler is operated the tunnel for 20 years. Today it's operated by the Public Roads Administration in Iceland. This is the longitudinal section of the tunnel. You can see we had an inclination of 8% here, which would not have been allowed today. It's almost 6 kilometers of length. We have a minimum rock cover of 38 meters and 40 meters waterhead here. The interesting thing, for those of you who know Iceland, we were talking about seismicity. This is in a location where seismic events take place. I'm not saying daily, but very, very often, very, very frequent. So we know that Iceland is cut by the North Atlantic Ridge, which is, Iceland is still growing because of the rift activity. And the project site is located some 10 to 40 kilometers west of the so-called Reykjanes volcanic zone. So it's quite active, and you have probably seen news flashes from Iceland where you see volcanics flowing on the surface of the country. And this is actually prone to active seismic activities. We did a risk analysis before the construction work started, looking at all sorts of events, 50 years, 100 years, 1,000 years, 5,000 years period. And we ended up with the conclusion that if we were going to do something, we should look at the 50 years seismic event. That is something that we had the possibility to cope with. If you go further with 1,000, 5,000, you have to do things that is not viable for a tunnel project. And in Iceland, the media was on top of us. They called it an engineering fiasco before we started. An engineering fiasco. That's not very nice to do a project which is believed to be an engineering fiasco. But as I said, we did a whole lot of risk analysis and things like that. We engaged the contractor on an ordinary build and operate and transfer for an operate and transfer after 5 years. We used adjustable fixed price construction contract. The contractor performed all detailed design and a comprehensive as-built documentation. What was actually coming out of that was that it was done in 2 years and 3-4 months, half a year shorter than what actually expected. We encountered water that reached a temperature of almost 60 degrees Celsius. 60 degrees Celsius with lots of concrete is a challenge. It was supported ordinary rock balls and sprayed concrete. The main thing here is also continuous probing ahead of the tunnel phase, always. It was designed for an optimistic 2,500 annual average daily traffic. At the peak, we had more than 6,000 vehicles through that tunnel. The tunnel, which was considered to be an engineering fiasco, was paid back in half the expected time or something like that. We had on one side of the tunnel, there was a station that is actually measuring seismic events. And one earthquake reached almost 6 on the Richter scale, and there was no harm on the tunnel. People who were in their cars during the event didn't even notice that an earthquake had taken place. They were asked, well, did you notice that there was an earthquake? An earthquake? No, not at all. And there was no damage to any of the installations in the project. Now I'm kind of running a little bit out of time, but and this has continued to meet the requirements of the society in Iceland. Now they're looking at making a second tube because the traffic density has increased so significantly. Then we go to the Faroe Islands. The Faroe Islands is a group of around 20 islands. Used to be connected with ferries between the islands, and people used to spend a day or two when they went visiting friends in the upper part if you live down in the southern part here. I shall bring you quickly through this. Low traffic. So what we have done, I have had a great pleasure of being the owner's advisor on all this tunnel project. This is where the airport is located, International Airport. This was the first subsea tunnel. Then we built one over here. Then we built one here, and one here. And now the fifth one will be the one which is connecting this island with the southernmost island. That means that people who are living down here will go the whole way up to the northeast in a couple of hours. And that used to take a couple of days earlier with ferries and things like that. So this is an infrastructure revolution. These are from, this is almost 5, this is almost 6, this is 11, and this is almost 11 kilometers long. And this will be 23 kilometers long. I hope I can say when it will be excavated, and not if it will be excavated. Yeah. I think I'll, well, as I said, there is a lot of different ways that we have available as far as gaining information about the substrata structures. We are often starting with acoustic seismic profiling, which means that you are able to cover a large area within a very short period of time. And that is used to identify where is the best location for this tunnel with the lowest water or sea level, yeah, and things like that. When you have fixed the alignment, this is for one particular tunnel project, when we have fixed the alignment, as we have done here, almost, we have some variations, but basically along the same route, you are doing refraction seismic profiles, as I said, which is something that you lower down on the seafloor, and you do it with explosives to be able to actually capture whether or not there are fault zones or things like that. And you will also have a identification of the rock mass ground conditions in terms of seismic velocities. And of course, core drilling, we could probably have done a directional core drilling from here, for example, to be able to reach the central part of it. Yeah, I think I'll say thank you for your attention.